Good to go whenever you're ready. Just watch the table. Please don't trip over.
Good afternoon, everyone. I'm Josh, and today I'll be presenting my findings for my master's research project titled From Point Sources to Phantoms, Refining Dose Rate Models in Nuclear Medicine with Technetium-99M, Fluorine-18, Iodine-131, and Lutetium-177. My supervisors for this project are Mario, Christine, Rick, Paul, and Benjamin. So when patients are administered radiopharmaceuticals in nuclear medicine for diagnostic scans or therapies, they become sources of radiation external exposure. And sometimes patients will require consultations, ultrasounds, or even hour-long surgeries shortly after their procedure, meaning that the patient is still radioactive. This obviously raises concerns with non-radiation healthcare workers, such as sonographers, who are interacting with these patients. The healthcare professionals performing the procedures will be closer to the patient and therefore be exposed to higher amounts of ionizing radiation. So traditional dose rate estimates assume the patient to be an unattenuated point source and apply inverse square law calculations, both of which tend to overestimate exposures, particularly at closer distances. Therefore, it is necessary to quantitatively estimate the dose to healthcare workers during these procedures at clinical distances by using more representative radioactive source models and obviating the need to use inverse square law scaling. This then enables healthcare providers to make evidence-based decisions regarding shielding requirements, close contact restriction periods, and the timing of procedures for recently treated patients. With the rising adoption of diagnostics, staff will undoubtedly come to repeated close contact more often, increasing their total radiation exposure burden. So the aims of this project. So the first aim of this project is to design an inexpensive, robust and reproducible setup to measure dose rates from different radioactive sources. The next aim is to validate the robustness and reproducibility of the setup by measuring point source models of different radioisotopes and comparing them with the relevant literature. Then we move on to measuring real-world dose rates at patient-relevant distances, so from 10 centimetres to 100 centimetres. Including the line sources and phantom source models. Then by using the point source measurements, the results and the phantom source results, I can calculate self-absorption factors to support radiation safety in nuclear medicine and risk assessments. So this is a schematic diagram of the experimental setup. So in order to obtain high quality measurements, measurements need to take place in an environment where there is very minimal radiation background levels and also minimal backscatter. So inexpensive materials we use, such as extruded polystyrene and PVC sheets. The extruded polystyrene is mostly air, so this was chosen to mitigate scattered radiation effects. The setup was also elevated 120 centimetres above the floor, and this was to prevent backscatter from the hard floor. And finally, the measurements took place in the centre of the outpatient room at Medical Technology and Physics here at Charlie's, and this was done to reduce the amount of scatter from the surrounding walls. So the detector used was a Fluke biomedical ionisation chamber survey meter, and it was secured on a sliding foam to ensure that the calibration point of the detector was level with the radioactive source, and the dose rates were recorded at each marked distance. This minimises human error and the interactions we had with the setup. So these are the two phantoms that we used for the phantom source measurements. On the left there, you have an in-house made neck phantom. So this was exclusively used for measurement of radioiodine. So this phantom is made of PMMA, and it represents a nuclear medicine patient receiving radioiodine treatment, so for hypothyroidism or thyroid cancer. You can see that there's an insert there for where we place the radioiodine salt for physical measurement. Three orientations of the phantoms were considered, so anterior, posterior, and lateral. For the neck phantom, the anterior and posterior orientations were measured from the center of the source, and the lateral orientation was measured from the center of the phantom. This was done to avoid weird geometries. The other phantom is a NEMA IEC phantom. This phantom was used for measurement of all the other radioisotopes. This phantom represents the abdomen of a nuclear medicine patient. Typically, it comes with spheres and a lung insert, but these were removed to make the phantom a homogeneous mixture of water and radioisotopes. And all the orientations were measured from the center of the phantom. So this is some aerial shots of the experimental setup. So in this study, we investigated point sources, phantom sources, and light sources. So as the title suggests, the radioisotopes used in this study were technetium-99M and fluorine-18. So these are two radioisotopes that are most commonly used in nuclear medicine for diagnostic scanning, as well as iodine-131 and lutetium-177. These are the two radioisotopes that are commonly used for therapies and theranostics. So once I jotted down all the data, I then entered it into Microsoft Excel, where I performed all my data analysis. This included decay correcting the data for the time at which they were recorded. So this was particularly important for the radioisotopes with short half-lives, so technetium-99M and especially fluorine-18. I also normalized the data to activity and calculated averages, standard deviations, and standard errors. I then imported all that data into MATLAB to generate my plots using MATLAB's curve fitting tool. I used a bi-exponential nonlinear model fit following this formula with inverse variance weighting. So I applied inverse variance weighting to best model the measured data. So due to the nature of the data, as the distance increases, the standard error of the measurements decreases. So it made sense to apply more weight to those values with less uncertainty. And this better represented what I physically measured, as well as also improved the accuracy when comparing with the literature. And finally, all the models were stored in Mathematica, where I performed my calculations for gamma factors and the self-absorption factors. So self-absorption. The self-absorption factor refers to the loss of emitted radiation within the source material itself. So I calculated the self-absorption factors for each orientation of the phantoms, as well as an average self-absorption factor value. So the average one is very useful in circumstances where you're interacting with a nuclear medicine patient with unknown geometries and unknown circumstances. So I got an average and a standard deviation were calculated from 91 self-absorption factors covering the clinical range from 10 to 100 centimeters using this formula. So the attenuated dose rate comes from the phantom measurements, and the unattenuated dose rate comes from the point source measurements, both at the same distance. So moving on to results and discussion. So the gamma factor is the external dose rate which is specific to the radionuclide. So in this case, technetium-99M. So I estimated the gamma factor by evaluating this normalized dose rate curve at 30 centimeters and 100 centimeters, and then compared with the relevant literature. So in this case, it was Delacroix, which the radionuclide data handbook. So this is the globally recognized gold standard when it comes to published values for gamma factors. And you can see that my results at both two clinical distances, so 30 centimeters and 100 centimeters, were within 10% of their value. So there was strong agreement. This is the self-absorption factor graph. So this shows the self-absorption factor for each orientation of the phantom and the average. And I also have put self-absorption factors which have been published by other literature for comparisons. So the self-absorption factor for technetium in the lateral orientation best agreed with Monte Carlo simulations performed by Hum. And you'll notice that for all the radioisotopes used with the NEMA phantom, the lateral orientation was the orientation with the most attenuation. And these were the results that were most comparable to Monte Carlo simulations and patient measurements. So the lateral, anterior, and average self-absorption factor values all lie within 2 standard deviations of the self-absorption factor value reported by year. So these come from patient measurements. And this is due to the significantly large standard deviation, which demonstrates high levels of patient variability. So some reasons why there's high levels of patient variability is that all nuclear medicine patients have varying levels of tumour burden. They also have different retention rates of the radiopharmaceuticals. And also the BMI of patients is also significant as well. So it's been well documented that there's a statistically significant inverse relationship between the BMI of a nuclear medicine patient and their external exposure to rate. Moving on to fluorine-18. So you can see that when comparing with Delacroix again, there was also strong agreement. There was a bit of an improvement compared to technetium 99M, with both values being within 5%. So I suspect that this is because of the emissions from technetium 99M, the higher 511 keV photons. So the detector is picking up more signal. Same as technetium, the self-absorption factor in the lateral orientation best agreed with patient measurements by year. And the average self-absorption factor, so this is the factor that accounts for unknown geometries and unknown circumstances, agrees with the literature. So this is a good result. Iodine 131. So iodine 131, we actually had the best value when comparing with Delacroix at 30 centimeters, within 1% of their value. It was a little bit less close for at 1 meter. Although when comparing with other literature sources, there was strong agreement. So our value lies in between the Canadian Nuclear Safety Commission, the value that they report, as well as Wasserman and Glenmore's value. So the self-absorption factor for the anterior orientation is close to unity, which is expected, because if you remember from the earlier slide, the neck phantom, there's very little attenuation between the source and the detector. So this makes sense. It should be very similar to the point source. Now, in reality, treating the thyroid activity of a radioiodine patient is actually quite realistic. The posterior self-absorption factor of the neck phantom agrees with patient measurements. So for this phantom, that was the orientation with the most attenuation. You see that the value published by Hum lies in between the posterior and the average self-absorption factor values. But because of the anterior self-absorption factor is heavily skewing that average up. So if you were to ignore that value, the average would be much closer to Monte Carlo simulations and also patient measurements. So this is just a short summary of the gamma factor results, which come from the point source measurements and their comparisons with Delacroix. You notice that most of the literature values, they publish a value at either 30 centimeters or 100 centimeters, disregarding the entire clinical range. So if you want to estimate the value at a distance that isn't 30 or 100 centimeters, you have to use the inverse square law. And many sources have demonstrated the limitations of using the inverse square law, particularly at close distances. So overall, the gamma factors were in excellent agreement with internationally recognised values in the literature, demonstrating that they can be experimentally reproduced to a high degree of accuracy using a simple, cost-effective setup. So you might have noticed the gamma factor values published by Schlein are significantly higher than the values in this study. So our value is within 28% of their value for both technetium 99M and I-131. And you'll see in the next slide, 29% for lutetium. So the reason for this is explained by the AAPM task group for the case of fluorine-18. So the way they measure it is the maximum dose received in a 30 centimetre slab of tissue from a beam of 511 keV annihilation photons. So obviously this incorporates additional exposure from the side and backscatter components. So lutetium, there was less literature available for lutetium when it comes to gamma factors. Although I did make some comparisons with literature at 1 metre, so within 10% of the Canadian Nuclear Safety Commission's value, and also within 5% of Los Angeles. So similarly to previous results, the lateral orientation is the closest to published values by Bellamy. Now, interestingly, Bellamy, they report the self-absorption factor using Schleing's gamma factor. So I just explained why that gamma factor is substantially higher. And that study claims that in the absence of patient measurements, when they're not available, a suitable lower value could be used, just like the one that was obtained in this study. So having this data for different source models and different radioisotopes across the entire patient-relevant clinical range is highly valuable. The main advantage of having this data is to quantitatively justify delaying procedures, such as ultrasounds and surgeries, to reduce occupational exposure. These values would be of sufficient accuracy for dose estimations in clinical environments, yet they're still conservative enough to ensure safe practices are being met. Limitations. So the main limitation of this study was the inability to calculate self-absorption factors using the line source model, and this was due to the field of view limitation. So at closer distances when measuring the line source, the value that the detector was picking up was underestimated because the detector was only seeing a fraction of the entire line source. Also, phantom measurements are not directly comparable with patient measurements. This is because of the non-uniformity of the radiation field surrounding a nuclear medicine patient, as well as the phantoms in this study represent simplistic cross-sections of human anatomy. So uncertainties, the main uncertainties with this study come from the detector itself. So this graph up here, that shows you the energy dependence from different emissions. So the lower energy emissions from lutetium and technetium, they were underestimated by less than 5%. For iodine-131, they were underestimated by less than 2%, and there was negligible energy dependence for fluorine-18. The average error associated with dose rate calibrations for the detectors was negative 2.91%, and the accuracy was plus or minus 10%, with precision being within 10% as well. The other source of uncertainty comes from the dose rate, the dose calibrator. So this is when we're measuring the activity of the radioactive sample. So both the electrometer accuracy and the system linearity is less than plus or minus 2%. So just to conclude, an inexpensive, robust and reproducible setup was designed to conduct a comprehensive quantitative study of dose rates commonly used in nuclear medicine using different radioactive source models. The gamma factor results from this study were consistent with internationally recognised results, with any larger discrepancies between results being explained by different methodologies used. The self-absorption factor value results are slightly higher than the literature, which appears reasonable due to the differences in phantom attenuations. And all the formulas for this study are provided, so this alleviates the need to use the inverse square law. So future directions. So I think future studies should focus on expanding the data set to include additional radioisotopes, so maybe like gallium-67, 68, indium-111 and terbium-164, as well as incorporating different patient geometries and also validating these results with in vivo measurements. I would love to see this data implemented into a user-friendly software tool, which would then allow staff to estimate dose rates in real time, supporting personalised, practical and efficient decision-making in clinical environments. Monte Carlo simulations is an incredibly useful tool, which I think could address some of the patient variabilities we see in the literature. So I'd like to thank my supervisors for their support and guidance over the course of this project. Also the staff at Medical Technology and Physics for letting me use their outpatient room for all my measurements. Also the staff at NUCMED and the PET Centre and Rapid for letting me use their facilities to prepare a lot of the samples for my measurements. Also Adriano for engaging in statistical discussions. And the UWA Medical Physics Research Group, including the students. Thank you for listening.
It's great. I was just wondering with the, so you mentioned that the data would be used potentially to delay procedures that would involve workers coming into contact with people who are emitting radiation. Is there also some clinical data? Because I assume those workers would be wearing dosimeters that could be used to, compare and also justify delaying those procedures.
Like in vivo measurements, like TLDs and stuff.
Yeah, well, I mean, like you mentioned that it might be used to delay like a patient getting an ultrasound right after they've been injected with the radiopharmaceutical. I'm saying that those workers who do the ultrasound, are they wearing dosimeters? So
sonographers, they're not usually monitored.
Right, okay.
They're unmonitored.
So there wouldn't be any dosimeter data that you could sort of look at and say, okay, they're getting this dose.
There have been some studies that are specifically looking for just the dose to sonographers. But typically the TLD measurements that I see in the literature are for like NUCMED technologists.
Right.
Because they're
It's
interesting.
People are online, they're at the same distance,
Yeah.
they're changing, and we can compare it with any distance. We can get the care.
Yeah, no, but
But we
like,
can get overall
Yeah.
situation. Yes, you're right.
but if they were wearing a dosimeter like that, you'd be able to know what dose they've got this to the skin, right?
That's right, time and distance
Mm.
is one, but we don't have any legal.
Yeah.
Actually, maybe we can take.
Maybe it's to justify having the error as well. Yeah,
Yes.
yeah. Like you'd say, actually, you might be getting this dose. You should wear dosimeter. Okay. Any other questions?
Yeah, maybe one question. Okay. I think, I don't know if you mentioned this, but you said you want to maybe repeat the same measurements with other radioisotopes. What were those isotopes?
So I mentioned like gallium 67 and 68, those are commonly used as well in scanning. I think terbium 164 is like a promising radiopharmaceutical at the moment because it emits Auger electrons. So it's exciting.
What? Thanks.
You said it's different for different patients. So what factors do you think could play, and could you simulate some of them in phantoms, like for future studies? Like you mentioned, patient geometries, what other factors could potentially affect?
Yeah, so I mentioned tumor burden, and you can sort of represent that in phantoms. So the phantoms, they do come with spheres, and so these represent metastatic hotspots. So you can attempt to represent this, but yeah, other patient factors such as BMI affects the external exposure. I think Monte Carlo is something that can definitely help. I've seen a lot of literature that looks at these patient-specific factors and how you can address them, and I think a lot of them use Monte Carlo.
Thanks.
Question if there's nothing online.
Go for it. Yeah.
Sort of builds off Ash's one actually. I find it really interesting the correlation with BMI. Because I mean that's like a historically pretty naff metric to be honest, because it doesn't account for body composition at all. But it makes me think that maybe that's suggesting that you could plumb into that a bit deeper. And if you could have a more robust metric that characterises the patient's body composition better, then that would be more strongly correlated and then could even better inform what's going on here. Do you agree, or do you think that's an avenue for?
Yeah, absolutely. I think this research is very much a stepping stone to a much larger project where you do consider all the other limitations that you have to consider when you're dealing with nuclear medicine patients. So yeah, definitely. That was just one study that they exclusively looked into BMI for lutetium patients, and that was their findings.
Yeah, really interesting. We can see what else.
Because the other option is multicolor modeling. Estimation of those, some the distance and time that people spending and the CT, BMI, I mean CT structure.
You could make it patient specific.
That's
Yeah.
But lots of room for open nutrients. Lots.
Great, thanks, man.
Brilliant. I think we're going to have to call it there because there's another meeting straight after this at 2. So good job, Josh. Thank you.
There's another meeting right